Hi, my name is Neal Damani, and this is my Lab 5 Sounding Magnetic Braking with Faraday for Physics 2212. Our goals are to collect observational data of a magnet falling through a conductive tube of aluminum foil, to model the magnet falling through the aluminum foil tube computationally, and then to compare the computational model with the observational data. Our findings are that the average time for the magnet to fall through the tube is 0.724 seconds. When there's a magnetic dipole of 1.4875, the predicted time for the model is 0.435 seconds, and then when there's a magnetic dipole of 2.166, the predicted time matches the observed time, which is 0.724 seconds. One of our key concepts is Faraday's law, which relates the integral of the dot product between an induced electric field and the length of the outer edge of a closed area to the negative derivative of the magnetic flux. Some of those equations are shown below. And then our other key concepts include the magnetic force on a wire loop, which is equivalent to the cross product of the current multiplied by the L vector with the magnetic field, where the L vector has a magnitude equal to the length of the wire. Another key concept is Newton's third law, which is going to be that the magnitude of the magnetic force in the loop is equal to the magnitude of the force on the magnet by the loop and opposite in direction. And then Ohm's law and its relation to Faraday's law, which states that the current is related to the quotient of potential difference in resistance. And some of this all is shown below in the equations. For a visual model, our system is going to be the falling magnet. Our surroundings are going to be the aluminum foil tube and the earth. Our F1 is going to be the magnetic force on the loop, and that's the downward pointing purple arrow. Our F2 is the upward pointing purple arrow, which is going to be the force on the magnet by the loop, which is going to be due to Newton's third law. And then we assume that the only forces acting on the magnet are the force of gravity and the force from the loop. And the model assumes the magnet falls with the north pole facing downwards. For a procedure, we had to mark the north pole on the magnet, measure the mass of the magnet, measure the width of the foil, the inner radius of the tube, and the length of the tube for the aluminum tube, drop the magnet through the aluminum foil a few times to record the magnet, and determine the time from the magnet entering the aluminum tube to the time the magnet leaves the aluminum tube, computationally model it, and then compare the observational results with the computational results. Our observational results are listed in the chart. The time between magnet forces entering the aluminum foil tube and when the magnet leaves the tube is going to be an average time interval of 0.724 seconds. The length of the tube being 0.46 meters, the width of the aluminum foil being 0.003 meters, the inner radius of the tube being 0.0135 meters, the total radius being 0.0165 meters, the magnetic dipole being 1.4875, and the mass of the magnet being 0.024 kilograms. Here's where we establish our initial conditions and constants, our magnetic field and magnetic flux, our simulation loop, and this is all for our computational model. And here's our computational results, or a graph of what our output was. Going into the discussion, the magnetic dipole moment found in Lab 3 was used. The simulation predicted that the magnet would take 0.435 seconds to pass through the tube. When the magnetic dipole moment is increased, the simulation predicted that it would be 0.724 seconds to pass through the tube, which suggests that there's potential that the magnetic dipole moment found in Lab 3 may be inaccurate, and that 2.166 ammeters squared might be a more accurate value for the magnet dipole moment. Some of the possible sources of error are going to be contact friction, air resistance, timing errors, and measurement errors. These would all potentially affect the speed of the magnet or could be inaccuracies in our measurements. For the what if, the resistivity of the conductor were reduced as close as possible to zero. How would the dynamics of the falling magnet change? Resistivity is directly proportional to resistance, so nearly zero resistivity would mean a nearly zero resistance. Nearly zero resistance would lead to a large induced current I, according to Ohm's law, as the current is inversely proportional to the resistance. Current's related to magnetic force by I times 2 pi r b sine theta, so a large current would mean a large magnetic force on the loop. By Newton's third law, the force on the magnet by the loop would be large, and the final effect would be that the magnet would fall with a lesser speed, falling slower and taking up more time because the force on the magnet from the loop would be much closer in magnitude to the gravitational force. And then for our second discussion, if there were holes or slots that were cut into the tube, how would it affect the ring currents in your model? Holes or cuts would disrupt the continuation of the rings of the aluminum tube. These rings are what allow the induced current to flow around the tube as the magnet falls. Disrupting these rings would reduce the induced current. The induced current is related to the magnetic force. As a result, the magnetic force by the loop decreases, and the force on the magnet by the loop decreases given Newton's third law. So our final effect would be that the magnet falls with a greater speed, taking less time, because the magnitude of the force on the magnet is much less than from the force of gravity.